Okay, anybody have that problem in front of them? Oh, we did that. It's in the notes from Monday. Yeah, exactly. Someone had to say it. Anything else? Any other ones? Okay, well, I'm going to just do another example with a truss, and I'm going to do it both ways, the way that we did it mainly in statics and the way that anybody, well, you all took statics with me, except Naomi, who is taking statics. But and then I'll do it with the truss simplification. It's probably good to be exposed to both of them, but so here's the problem. Oh, and then next time we'll get into internal loads, which is going to be along the path towards calculating stresses in beams. So that's what we're heading towards next. All right, so let's say we have a pin joint on the left and a beam like that, and then a mirror image on the other side, so a beam on the right connected to a pin joint. And these two are connected to each other by a pin joint. Let's say the length here is 1 meter, because the math is easier. If I designed like actual engineering structures, every piece would be 1 meter long and weigh 10 kilograms. And these angles are 20 degrees. And then there's an external load of 5,000 newtons. Okay, so I'm going to first do it the full way, the way that we did it in my statics class. And then I'm going to do the simplified truss approach, which is how I'm sure you guys did this kind of problem in your statics class, you two guys. So I'm going to start out by labeling this member 1, this member 2. Oh, that's a good question. The stresses. So we're trying to find stresses in each member. And then from there, you could go on and find the principal stresses. Well, since this is a truss, the principal stresses are going to be the stresses. And then we could find the max shear, we could find the strain, anything we want. Once we find the stresses in those, we can get all the other stuff we've discussed. All right, so I'm going to isolate member 1. Okay, so the idea here is 2 approaches. The general approach and the truss simplification. So the first one is the general approach. Okay, and let's, before I do this, who wants to give some of what are the benefits and drawbacks of these 2 different approaches? So this general approach, the one we did in my statics class, what's the benefit? Is there only one? Yeah, so the general thing is like, no matter what this structure looked like, if it's capable of being solved by statics, you could do it with this one approach, okay? this is a truss because we don't have any masses for the members. And so we can use the truss simplification for this. But if these did have significant masses, that's not much of a change to the problem, but then we wouldn't be able to use the truss simplification. We'd still be able to use this general approach. So that's the strength of this approach. The downside of this general approach is we'll see we have a much bigger system of equations. It takes longer, you know. So that's right. It only works in systems where every member is a two-force body. And that's a pretty serious restriction, you know. Okay, so this one, I'll call this the joint A, B, and C. So member 1 has a force vector from the pin at A, call that RA. We're ignoring the weight. And now we have to think about what's going on at the pin. Whatever is happening at the pin, we have to associate with just one of the members that's connected at that pin. And so what I'm going to do is, the way I keep it straight in my head, is I just always treat the pin as if it's part of the lowest numbered member. So this pin at B connects member 1 and member 2. That means I'm going to assume that that pin is connected to member 1. So anything that happens to that pin happens to member 1. All right, well, that pin at B, what's in contact with the pin? Yep, member 2 touches it, so there's a force on 1 by 2. And then there's also the 5,000 Newton force applied to the pin. And that's it. And I'm going to make the about point here, I guess. You can put it wherever you want. And now we'll just go through those forces. I'll write out the row vector, the force vector, and the moment. So the row vector for F12 and the 5,000 Newton force are both 0. So first I'll do F12. Cross product gives you a moment of 0 in the z direction. And then for the 5,000 Newton force, there's no row vector. The force vector is 5,000, 0. Cross product is 0. And then we'll go down to RA. What's the row vector for that force RA? So we're looking for a vector that goes from the about point to here. So that would be 200 degrees. Yeah. That's right. Yep, that's right. So that's negative 0.940, negative 0.342. The force vector is RAX, RAY. And the cross product is negative 0.940 RAY plus 0.342 RAX. And now our first two equations just come from setting these equal to 0. That's Newton's second law. Adding those up and setting them equal to 0. And then adding these up and setting those equal to 0. That's the moment equation. So Newton's second law says F12x, F12y plus 5,000, 0 plus RAX, RAY. Yep. Mm-hmm. Yes. And even within reason, if systems like this are, well, for the part where we're trying to calculate the reaction loads, if these systems are moving, then you would use dynamics. I don't think I'm going to do any problems like that in this class, not that I remember. But once you get past calculating the external loads, even if the system has quite a bit of acceleration going on, you can pretty much always assume that it's static in calculating the stresses, because dynamic effects don't change the stresses very much unless they're very, very extreme, you know. Like imagine how fast you'd have to swing a steel bar around for the centripetal acceleration to produce significant forces in a steel bar. You know, remember, we're trying to calculate like when this steel bar is going to fail or something, you know. Yep. Yes. Yeah. And yeah, there are times that you would, there are cases where, like, if one of those things was a roller and this thing was accelerating, you would calculate those external loads based on the dynamics. We're just not going to in this case, but yeah, you would. But then when you went from that to calculating the stresses and the strains, at that point you would start treating it like it was static, because they're not going to have much of an effect. Okay. Yeah, I'm sorry. No, that's right. So that's Newton's second law, and moment equation. Add up the ones in orange. So we get P42 RAX minus 0.940 RAY is equal to 0. And so coming out of this first member, we have three equations, three useful equations. The first one says F12X plus RAX is equal to negative 5,000. The second one says F12Y plus RAY is equal to 0. And the third one says 0.342 RAX minus 0.940 RAY is equal to 0. So let's see what we have. For variables in these three equations that we're keeping, we have two x and y components, RA x and y components, and that's all. We have four variables. We have three equations, and so that means we can't solve anything yet. And so now we're going to isolate the other body. So free body diagram, body 2. So what do we have acting on body 2? The pin we are treating as if it's part of body 1, right? So the pin is not part of body 2. The pin is touching body 2, though. So we have a force on 2 by 1. Okay. What about the 5,000 Newton force? It's already accounted for, exactly. So we don't include that over here. That's a force that's applied to the pin, so it's applied to body 1, not body 2. That's right. So here we have F21, which is negative F12 by Newton's third law. And over here we have RC. Up the about point here. So rho F moment for each of the forces. I'll start out with negative F12. The row vector is 0. The force vector is negative F12x, negative F12y, and the moment is 0. And now the force RC, the row vector from the about point to where that force is applied is 0.940, negative 0.342. The force is RCX, RCY. And so the cross product is 0.940 RCY plus 0.342 RCX. These are for Newton's second law. These are for the moment equation. So Newton's second law says negative F12x, negative F12y, plus RCX, RCY is equal to zeros. And the moment equation says 0.342 RCX plus 0.940 RCY is equal to 0. So that's three more equations. Equation 4 says negative F12x plus RCX is equal to 0. Equation 5 says negative F12y plus RCY is equal to 0. And equation 6 says 0.342 RCX plus 0.940 RCY is equal to 0. Okay, so now we have a system of 6 equations. We had 4 variables before, F12 x and y, RC x and y. Before we had F12 x and y, RA x and y, and now we've added RC x and y. So we have 6 equations, 6 variables, and we can solve that with reduced row echelon form. You could do it by substitution, but it would be sort of a pain. And if you solve that system, you get F12 is equal to negative 2,500 and then 909.57. RA is negative 2,500, negative 909.57. And RC is negative 2,500, positive 909.57. And now we want to use these to calculate the stresses on those individual members, or those stresses at points inside the individual members. So I'm going to go back to the free body diagrams and put these forces in. On this member, at RA, we have negative 2,500, negative 909.57. Using the tangent, you could figure out the angle that that's in, and it's exactly in line with this member, which is what it has to be in a two-force member. And the magnitude is 2660. And then up at this point, there's a force F12 acting, plus a 5,000 Newton force in the positive x direction. If you add those together, you get positive 2500, positive 909.57, and that's 2660 going in the opposite direction.
Then for our A, why is it going 2660?
So I could have written that as, well, you know, I could have written that as a vector with those components.
Yeah.
But it turns out that that vector with those components is, like, if you take the magnitude of that force, take the square root of the sum of the squares, it comes out to 2660, and it's exactly in line with this. You know, you could calculate that angle, use trigonometry to calculate that angle, and you would get that it's right in line with that member.
Yeah.
And then you'd think, oh, I should have, you know, recognized that because I know there's only two forces on this member. That means that they have to be either pure tension or pure compression. Yep.
Is that last one? Will those both be negative?
RC?
Yeah. What the direction? Equation 6.
So that is not on this member. That's on the one that's going this way. And so here, that's saying that way and that way. So this one's going to be in compression.
No, I just mean equation 6 for our setup of this one. It's the cross product of 0.940, negative 0.342, and RCX and RCY. Wouldn't that cross product be negative 0.342 RCX minus 0.940 RCY?
I think this looks right.
Okay.
Now, how did you get that 2660 again? I was trying to.
Oh, okay. That's just the magnitude of this force. So the magnitude is just, you know, negative 2500 squared plus, that's right, negative 909.57 squared, all square root, gives you 2660. Yep.
Why are we saying are you just saying
Well,
the Pythagorean theorem is trigonometry?
no, the Pythagorean theorem gives you the magnitude.
You need to
The trigonometry, like, there are two ways to figure out the direction. One is to recognize that it's a two-force member, but that's easy to miss sometimes. You know, you're not always thinking about that. Well, here's something that'll help you not miss that on problems like this, is the only kind of stresses that we've talked about for structures yet are for structures where the members are all two-force members. So for these kind of problems, you know that whatever forces there are have to be along the line of the member.
Why is it not compression?
Well, you can sort of, I think, kind of makes sense if you look at what's happening. This 5,000 is pulling that way, so it's stretching this one and compressing this one. Okay, so the other member looks like that. And that one has negative force F12 acting at the top. So that's positive 2,500, negative 909, which is this with a magnitude of 2660. And then the other force is this direction, 2660. Okay, so that's the general structures approach to this problem. So now I'm going to do it with the truss simplification. And it's going to be significantly faster to do. This takes the extra work of classifying the type of structure you have. And then if what you have isn't a truss, you can't use this approach at all. So for the truss simplification, I'm going to isolate the pin at B. So free body diagram of pin B. and we have two members touching the pin. So we have a force going parallel to member 1. We'll assume it's in tension. If we get a negative, that means it's in compression. I'll call this one F1. And then we have a force along the line of member 2. Call that F2. And then we have the 5,000 Newton force applied externally. And so Newton's second law for this says we have F1 times the unit vector in that direction. So that's F1 times 0.940, negative 0.940, negative 0.342. We have F2 times the unit vector in this direction. So that's positive 0.940, negative 0.342. Then we have 5,000 in the positive x direction. And all that adds up to 0. So we have one equation that says negative 0.940 F1 plus 0.940 F2 is equal to negative 5,000. The second equation says negative 0.342 F1 minus 0.342 F2 is equal to 0. That's two equations for two variables. And if you solve that, you get that F1 is positive 2660 and F2 is negative 2660. And the interpretation of that is that the member on the left is in tension because it's positive with a total value of 2660. And the member on the right is in compression. So you have 2660 like this. Any questions about that?
How does the F1 compare to the free body diagram? You know, because it's positive, but now we're saying that the arrow is pointing the other way.
Well,
So
if using this truss simplification, if you get a positive number, it means the forces are away from each other, parallel to the member. And if you get a negative number, it means the forces are towards each other, parallel to the member. Right, it's not a vector direction. It's just saying positive tension, negative compression. Any other questions about that? Yeah, right. That's right. Yeah. It is like that. Anything else? All right, so now the good news is they agree. If they didn't, that'd be terrible. Well, I just had the answers written down. I guess we didn't really solve them, so I don't even know if the equations come out to say that. But they do if you do them right. But the answers agree. And so now we have to calculate the stress. Oh, and I didn't give cross-sectional areas. Let's pretend I did. Cross-sectional area of each of these members. So let's assume it equals 0.001 meters squared. Okay, so the stresses for points in member 1, and I'm going to do it now with, think about it with the x-axis along the length of the member in each case. So we're doing this for different coordinate systems for each of the two members. So the XX stress for member 1 is positive 2660 divided by 0.001. And so that is 2.660 times 10 to the 6 pascals. So the stress tensor for member 1, that's the only non-zero stress. So the stress tensor is 2.66000, everything else is 0. And this is times 10 to the 6, so that's megapascals. And then for member 2, the XX stress is negative 2660 divided by 0.001. So that's negative 2.660 times 10 to the 6 pascals. And so the stress tensor, number 2, is negative 2.66000, everything else is zeros. Megapascals.
Perhaps we'll go over this.
Mhm.
But what would be the middle eigenvalue in this case?
0.
But are you going to have two zeros and another number?
Yes, and so what that means is you could do your rotation if you were trying to calculate the stress tensor with the maximum shear. You could do your 45-degree rotation around, in this case, the y-axis or the z-axis. You'd get the same thing. Okay, so let's calculate the max shear in 1. The maximum stress is 2.660 times 10 to the 6. The minimum stress is 0. Divide by 2, and you get a maximum shear stress of 1.330 times 10 to the 6. The max shear stress for member 2 is 0 minus 2.660 times 10 to the 6. 0 minus negative, sorry. And so you get the same thing, 1.330 times 10 to the 6. And what are the principal stresses? Can anyone do that eigenvalue problem in their head? Somebody can. That Ryan can.
Well, the principal stresses are right there.
That's right, exactly. So the principal stresses are, for member 1, the principal stresses are 2.66 times 10 to the 6, 0, and 0. Because this tensor here doesn't have any shear stresses, so that's already a principal stress tensor. And for member 2, the principal stresses are negative 2.66 times 10 to the 6, 0, and 0.
Why don't we write the
I wrote megapascals instead of pascals,
yeah.
so that means times 10 to the 6. And how do you calculate the strains? You wanted the strains. So yeah, you'd have to know what E and nu are for this material, whatever it is. You know, if it's copper or something, you just Google that, find the E value and the Poisson's ratio for copper, make the compliance matrix for it, and then multiply the compliance matrix times the Voigt form of this stress tensor. Let's see. Okay. Any questions about any parts of that problem? Well, I just can't help avoid giving like a little plug for doing the general method. So what would you do if you wanted to calculate these external loads? If, like, what would change if now we said, oh, okay, now we want to do this problem, but to make it a little more realistic, each of these two have a mass of 20 kilograms. Okay. Well, the general method wouldn't change at all. You just, for each of these, have a weight acting there. You do everything exactly the same. The truss method wouldn't work. You can't do it that way. You'd have to use a different approach, and the other approach that you learned that you would have learned as a companion to the truss method, the method of frames, also would not work for that problem. So just adding that weight, and there's no way, like in most statics books, to calculate that. But using this general approach, you can calculate it, and it doesn't even really change it much. Okay.
Would you, for the stress, would you still want to take the forces and get them into one, find the magnitude of those? Or would you use the vector?
Oh, so for these problems, you need to take the magnitude, and you need to figure out whether it's in tension or compression.
So you just
Okay.
take the magnitudes of those forces.
So yeah, like say that you got these answers out. So for this one, we drew these free body diagrams before, so we know we have RA over here. That's, you know, you can think of it as 2500 that way, and 909 this way. And then we have up here F12 plus another 5,000 in the positive X direction. So we have 2,500 like that, and positive 909. So first take the magnitude, you know, taking the magnitude gives 2660. And then just think about two vectors that you're adding up in these directions. Would they put this thing in tension or compression? You know, if you're going somewhere in this direction with those two vectors, somewhere in this direction with those two, so that's tension.
And then if there was like a non-negligible weight to the member, would that go into the for purposes of stress, would those go into those vectors?
We would not be able to calculate the stress yet.
Okay.
Because we're only doing stresses for objects that are loaded according to the rules of stress elements, and we haven't ever dealt with a stress element that has, you know what I mean? Right. Yep. I mean, when you add up two vectors that are perpendicular to each other, the sum has to be between those two angles. So you know that this can't be, you know, it can't be going that way, and this can't be going that way. So you know it's tension. That's just the way to think about it.
They just do the
Yeah, that's right. Exactly. And so, yeah, with the problem so far, all the structures you're going to see are trusses. And the reason they're all going to be trusses is because using that general method, you could solve other structures, but you couldn't calculate the stresses yet. that's going to be the next topic we'll get into, is how to calculate the stresses in beams, where you have other things besides tension and compression. Any other questions? Okay, so the next topic we're going to get into, next topic, stresses in beams. A beam, first of all, what does that mean? The beam is a long, slender member that is subjected to at least some non-axial loads. Okay, so in the truss problems, all of the loads that we had were axial. All the loads are parallel to the long axis of the beam. Beam problems could be made out of the exact same materials. The only difference is we know there has to be some kind of force or couple or something. It's not just going straight along the line. So if we had the same structure here and applied a force that way on one of them, that would make that a beam. Okay. So these are not beams in the current loading because all the forces are parallel to the axis. And we saw that when we calculated the external loads. You know, it was all tension, or on the other one, compression. Those are axial loads, you know, parallel to the axis. If we applied another force, you know, just a force that wasn't along that line, let's say we apply a force like that, then even though it's the same object, this would be a beam now.
And would that include perpendicular as well?
Yep.
Okay.
Yep. And there can still be loads that are parallel. There just has to be some loading that's out of that line. And stresses in beams depend on 4 types of internal loads. Those are tension or compression, shear force, bending moment, these are the only 3 types that we talked about in statics. So these are the internal loads from statics. And then there's one other type, torsion. Yep. And so, yeah, in statics, we talked about all these, and they mean the same thing they did before. The only difference is this idea of torsion, which is like if this is a beam, you know, this is the long axis of the beam, and you twist one end this way and the other end the other way, try to twist this thing, that's torsion. Okay, so that's going to be a new type of internal load that we're going to deal with. And so before we can talk about calculating stresses, we have to make sure that we know how to calculate those internal loads. And so this topic of stresses and beams, we're going to first go back through how to calculate internal loads, and we're going to include this new thing, torsion, this new internal load. And then once we've talked about internal loads, we're going to use those internal loads to calculate the stresses in the beams. Yep, it's going to be just the same, except that there's going to be this new thing, torsion. And it's not any harder to calculate the torsion or anything. It's just a new thing we're going to think about. All right. Yes? Oh, no, not yet. Then when you see it in statics, it'll be easy. Yeah, and actually, when you see it in statics, you should be like, why aren't we doing torsion? That's always the goal of any good engineer. Yeah. There's one other thing I wanted to say in the topic before. Let's see. Okay, so we got this. So we calculated these external loads, and then we use those to calculate the stresses. What points are those stresses valid for that we calculated? Anything but the ends. Yep, exactly. So we don't know anything about what's happening here, here, or the two ends of that. But everything in between the, far at the two ends has the same stress value, and it's equal to the ones that we calculated. Okay?
But internal load is like
Yes, internal loads are the loads applied to one part of the beam by the adjacent part of the beam. Yeah, we'll do that. But you know what? The good news is all this stuff that might have been kind of hazy the first time you saw it is going to be a lot clearer now the second time we see it. And we're going to go through almost the exact same approach, All right.